afternoon. So let us continue this Riemann integral lesson. But before starting, let me remind you what was the concept. So a little bit refreshing your memory. If we have a function defined on a closed interval from a to b to r, but it is bounded. So the whole theory of Riemann integrals were based on bounded functions. So we will not study improper integrals. So what will happen for definition of our integrals if the function is unbounded? You have studied that a little bit under the title of improper integrals in your calculus, but in this course we will not delve into it. So if we have this function, and then we had the notion of a partition. So if I have a partition, it means that I have a set of points. The first one is, we call it x naught, but it is a, and then I choose some increasing, some numbers in between x naught, which is a, and b, which I denoted, for example, by xn. But these numbers should be in a strictly increasing order, as then we call it a partition. For any partition that you choose for A and B, which we have infinitely many of them, one of them is very important. I mean, one of them has a special place, and that is the regular one. The regular one means that you choose these intermediary points in a way that the length of each subinterval is exactly the same. But in general, you don't have to work with regular partitions. So then what do you have? You define an upper sum of this function corresponding to that partition P to be defined in this way: sigma m, capital M sub k, delta x sub k. K goes from 1 to n. And then you define something similar, lower sum, which is sigma, this time little m sub k, delta xk. K goes from 1 to n. So if I ask you what is this capital M sub k, if you remember, it is defined to be the supremum of the values of the function where x belongs to the kth interval, subinterval. Yes, and then little m sub k is defined to be the infimum of that set. Now, of course, if you are working with a continuous function, there is no difference between supremum and maximum. There is no difference between infimum and minimum. Okay? And then if I ask you what is delta x sub k, it's just the length of the kth interval. This is your kth interval, so this is defined to be this. Okay, so we started with the bounded function on a closed interval, then we pick a partition. There are infinitely many of them. For each partition, I can I can find an upper bound, upper sum and lower sum defined in this way. And then, if there were two more intermediary steps, and that is the definition of the lower integral, which we denoted by that. For this function, what I need to do, I have to calculate all these upper sums and put them in a set. So it becomes the set of all upper sums such that P, and I told you, because this is a long sentence, when I write this, I mean P is a partition of A and B. So for simplicity, when I write this symbol and then P, please read it in that way. So this is a set of numbers, and we prove that this set is bounded above. So it has it's bounded below. Of course, it's bounded above, but it is bounded below. For my case, it is important. Oh, sorry.
Shouldn't it be supremum of the lower sum?
Yes. Thank you very much. This is the lower sums, and then I take supremum. Thank you. Okay, and then similarly, the integral, the upper integral, is defined to be the infimum of the upper sums. And then we showed that in general there is no guarantee that these two numbers are the same. For example, for Dirichlet function, we realized that one of them is 0, One of them is 1, regardless of the partition that I choose. But we've proved that this one is always less than or equal to this one, but there is no guarantee that they are equal. But in cases that these two numbers are equal, so if the integral, the lower integral and the upper integral are the same, then f is said to be Riemann integrable. Because Riemann integral is the only one that we studied, you just can say integrable because we also have different types of integrals. And then the common value is called the integral. Okay, this then the common value is called the integral of f on the interval a and b, and we just simply denote it by, and is denoted by just simply integral of f from a to b. But we'll also learn that if we want to prove integrability just using the definition, it's probably not that efficient. We want to develop some theorems that guarantees integrability in a more concrete way and more tangible way. So one theorem, I don't know if I have it on these slides. So this one is a very important theorem. I just stated that for you. Hopefully you have studied a little bit about the proof. I will take that for granted, then I will try to prove other ones that are common. So Riemann integrability criterion, so let me write it here for you. And so this will be 12.1. So, and by the way, this was the notation we use when we write this. This is another way to say that f is Riemann integrable there. And then you remember I also introduced this notation, curly C, A and B, so that this function is continuous on the closed interval A. Okay, so let me use these symbols to state this theorem. Of course, this is the complete sentence, but if you want to write it, it would say that f. So whenever I talk about Riemann integrability, I always assume that f is bounded because the whole theory is based on for bounded functions. So I would say that f belongs to this set. This you can read f belongs to this, or you can say that f is Riemann integrable on A and B if and only if any epsilon that I give you, you can find a partition P, a partition of AB such that the difference between these two become smaller than that given epsilon. This is called Riemann integrability criterion. So if you know f is integrable, then it is guaranteed every positive epsilon that I give you, no matter how small that is, we can always find at least one partition for which this difference can be made smaller than epsilon. In other words, in the other direction, if you can grant the existence of P, for every epsilon, if you can grant the existence of a partition so that this works, then you can immediately conclude that your function is Riemann integrable on that interval. But usually, when we talk about a generic partition, as I told you, there is no good regularity for it. because those points can be chosen completely arbitrary. So there are infinitely many of them, and they are not following a regular pattern. So working with something that is not following a regular pattern is not that easy. The question is that can we have a theorem so that instead of working just for any arbitrary partition, we can just only work with regular partitions, which are manageable, more manageable to work with? And the answer is yes. This is not in your book, but that's what I want you to learn because it will help us a lot. So this is Archimedes-Riemann integrability criterion. Applying this is much simpler than the original one. It is longer, but it is much simpler to work with in practice. Okay, so let me just explain it here on the board. So 12.2, is it 12.2? Yes. So there are two parts for the theorem. So let us write part one. So part one tells us that, again, f is a bounded real value function, so everything is bounded. If the functions are bounded, then f is Riemann integrable if and only if there exists a sequence of partitions. So let me write a sequence of partitions. So you might think that, okay, we are making the problem harder because in Riemann integrability criterion we need to find one partition, but here we have to find a sequence of partitions. But you see that in practice it will become easier to work with. So f belongs to R if and only if you can come up with any sequence of partitions, not necessarily regular ones, any sequence of partitions such that when you calculate this for any term of the sequence, this becomes a sequence in numbers, yes, because this is a number, that's a number. When you subtract them, it becomes a real number. So this is a sequence itself of real numbers. This is a sequence of partitions. Partitions are sets. So these are sequences of sets, but this is a sequence of numbers. So I can talk about the limit of this sequence. This is part one of the theorem. So it tells you that if you can find a sequence of partitions for which this limit is 0, then it is granted that your function is integrable. And the other way around, if it's granted that your function is integrable, it is always possible to find a sequence of functions with that property. So this is part one of the theorem. So part two of the theorem, if f is integrable, so if f is integrable, and we know that the limit of u fpn minus L fpn as n goes to infinity is 0 for some sequence, yes, and Pn is any sequence. So let me. So that's not a good correct way of phrasing it. Or over if f is Riemann integrable and Pn is any sequence satisfying this. So for some sequence Pn, then from these two you can conclude that, first of all, from this you can conclude that it is integrable, because for some sequence you have this, it is integrable. And the question is that what is the value of the integral? Then you can conclude that the integral from a to b of the function is equal to the limit of u f pn, n goes to infinity, and integral from a to b f is equal to the limit of L F P n, then n goes to infinity. Okay, so let us do it step by step, because this is a very simple theorem to conclude from the Riemann integrability criterion, but it is easier to use. So don't confuse yourself for the second part yet. So let us go to the first one. So proof, but I am taking the Riemann integrability theorem as for granted. Okay, so I want to prove number one, but I want to go in this direction. Okay, so I know that f is Riemann integrable. So f is a Riemann integrable. I want to show, yes?
Should we like look at the theorem as two separate theorems, or is it, or like
Yeah,
do you have to
I
prove
try
one
to-
and two to know?
It's two theories. I mean, it was not very instructive if I want to put them as two theorems, but you can look at it as two theorems.
Okay.
Yeah. So, but for the time being, forget about the second part. So what I want to prove is that if f is Riemann integrable for the first part, I want to prove for you that you can always come up with a sequence of partitions for which this limit is equal to 0. So I have to construct that partition for you. So, okay, so f is Riemann integrable. We want to prove that this sequence, there exists a partition for which this limit is equal to 0. Okay, I would say let n belongs to n. Yes. So f is Riemann integrable. Now I want to use the previous theorem, so theorem 12.1. What can I conclude? I can conclude that there exists a partition, which I call it P sub n, because I want to find one single partition for each natural number that you give me. So you give me a natural number, and I know that my function is Riemann integrable. According to this theorem, I can guarantee the existence of a partition for which u f of Pn minus L of f of Pn is less than 1 over n. Do you agree with that, what I have written? I just want you to understand what I have written is true based on 12.1. Yes? Because this tells me that for every epsilon, you can find the partition with this property, with this difference less than that epsilon. But now instead of epsilon, I am using 1 over n. 1 over n is also a positive number. So this theorem grants that there exists a Pn with this property. Is that right? But of course, I can always write that this one is also greater than or equal to 0. Yes, because we know that always upper sums are greater than or equal to the lower sums. So this difference cannot be negative on the one. Okay, so can you see we are done? What was my goal? My goal was to show you that this limit is 0 for some sequence of partitions. Did I find my sequence of partitions? Yes. You gave me n. For every n, I offered you a partition. So this means that I have offered you my sequence of partitions. But I want to prove that for that particular sequence, this limit is 0. But that's also possible, yes, because the limit of this one is 0. The limit of this one, when n goes to infinity, the limit of this one is also 0. So by squeezing theorem, the limit of the middle one is also 0. Squeeze theorem, yes? Limit of u f of Pn minus L f of Pn is equal to 0. But that's correct. That was easy. Part 1 from left to right. Now again, part one from right to left. Okay, so this time what I know that there is a sequence of partitions for which this works. My goal is to show that F belongs to F is Riemann integrable. So for Riemann integrability, I want to prove that for every epsilon, I can come up with a partition with this property. Then I can go backwards. So I would say let epsilon be greater than 0. Let epsilon be given. Okay, my assumption is that the limit, since limit of u f pn minus L f and pn is equal to 0, I would write something and then I will ask you, do you agree with this property that there exists an n, a natural number, such that u f of pn minus L of f and pn is less than epsilon? Do you agree with that? Yes? Because if you want to understand it better, we can call this a sub n, because that's a sequence of real numbers. I can give it the name a sub n. So then when you say that the limit of a n is equal to 0, what does it mean? It means that the distance between a n and this limit can be made smaller than any epsilon. That the only thing that I can do probably is to fine-tune this index so that after that particular index, this holds. Okay, so this is the existence of such an index is granted. And then we are done. Yes, that's my partition. So we are done. Any questions? That's because the limit of a sequence is 0. It means after there is no need for absolute value here because this difference is always non-negative. That is why you don't see that absolute value here. Okay, because this is always non-negative. And when I say that the limit of my sequence is 0, what does it mean? It means for every epsilon greater than 0, I can find an n such that if n is greater than or equal to n, then this is granted. That was the definition of limit of a sub n is equal to 0. Do you remember? So this means that for every index, so that the index is n or is capital N or greater than this one works. So it means that this also works for capital N. And I have written that for capital N. That's just exactly the definition. You see that that was extremely simple. But now, let us, for example, go to part 2. So part 2, I have two assumptions here. I know that f is Riemann integrable, and I know that the limit of u, f, and pn minus L, f, and pn is equal to 0. So let me prove one of them for you. I want to prove that, for example, a limit of L, f, and pn when n goes to infinity, it is equal to my integral. And of course, there is another one similar to that, but the proofs will be similar. So I have two ingredients now. So I know that my function is Riemann integrable. I know that for some sequence of partitions, accidentally or by educated calculations, I realized that this limit turns out to be 0 for some sequence of partitions p sub n. Okay? We want to prove that the limit of each one of them individually is the integral that I am looking for. Okay, so how can we prove that? So because f is Riemann integrable, if this means that the lower integral and upper integrals are the same. exactly as I reminded you today. Yes. So let us call these three numbers which are equal I. Okay, so let me call them I for simplicity of writing. Okay, so I know that this I is definitely smaller than this upper sum for any n. Yes, and it is greater than this lower sum for every n. Yes, this is what we saw before. So let us. So this is not a conclusion from here. So I have to stop here and then write this. Yes. How can we prove that? Okay. So now it is very simple. You know, I subtract this from all sides. So from here, I can conclude that. Let me add minus L, F, and P sub n to all these sides. This becomes 0. This becomes I minus L, F, P, n. And this becomes U, F, and Pn minus L, F, and Pn. Yes? So you see, in this problem, in this step, I know that my function is Riemann integrable. So I know all these three numbers are equal. I call this this common number I for simplicity of writing. So I is definitely less than this U, and then it is greater than this L for every n, not just for one particular n. So I am fixing one n, and I am writing this inequality for one fixed n, and then I am subtracting this number from all sides of this inequality, and I get this. Okay, but now again I want to use a squeezing theorem. So if I ask you what happens when I send n to infinity here, what happens? According to my assumption, this limit when n goes to infinity is 0. And this one is just a constant. When I send n to infinity, the limit is also 0. So this means that the limit of the middle sequence is also 0. So by squeezing theorem, what I can conclude that the limit of I minus L, F, P, n goes to infinity is equal to 0. But this is a constant. So this is a constant and this limit is 0. So this means that the limit of L, F, P, n is equal to I when n goes to infinity. And that is exactly what we wanted to prove, because I is another name for this. So that is exactly what I wanted to show. Okay, so this is the theory of that. And I want to make sure that even though this theorem is very useful, if I use intentionally the regular partition, but this is by no means implemented in the theorem itself. So any sequence, I will not have time to go through all the examples of the notes, but I have given you one nice example if you want to see that one partition that I am choosing is not even regular. The usual ones are the regular ones. So I want you to see how we can use this theorem to really calculate something here. Of course, the calculations, as you will see, still becomes long for very simple functions, and that is why we really like the fundamental theorem of calculus invented by Newton. So, and that was the reason that we are interested in primitive functions, finding primitive functions to calculate integrals. But for the time being, let us just assume that this is the only tool that we have in our hand. We want to do this example. Any questions here? Okay. So what matters for me is now I wanted you, of course, to understand the proof, but even if you didn't understand it that much, still you can follow the solution of this example, which is one of the important examples. It's very simple, but these kinds of exercises, I have put it in the notes, and I have actually asked you to solve some of them. So I have given you a function, f of x equals to x, extremely simple function. We want to show that it is Riemann integrable on the closed interval from 0 to 1, and I want to determine its limit. Its integral. So 12.3. So what do I have? I have a simple, extremely simple function, okay? And then it is defined on 0 and 1 only. So it is from 0 and 1 to R, which is of course bounded. And then we want to show that f belongs to the Riemann integrable functions on this one. So this is one question mark. Another question mark is that, okay, now we know it belongs to there. What is its integral? These are the questions we want to answer. But of course, you know that this is an extremely simple problem. Can you answer it based on your calculus knowledge now? Immediately, what's the answer to this integral?
1.
What?
1.
No. 1/2. Because a primitive function for x is what?
No.
A primitive function is a function whose derivative is x, which is x squared over 2. And then you put 1 and 0, it becomes 1/2 and 0, and you subtract them. So in a matter of 2 or 3 seconds, you can prove both integrability and its value. So that is actually the genius of Newton, who connected the integrals. You see, in this presentation, we didn't even define the notion of derivative. Okay, so it means that everything we have started with has nothing to do apparently with derivatives. So he was able to connect these ideas with the idea of derivative and find a simple way to calculate this. And that was a huge progress because, as you will see, if I increase this function, I will tell you. So let us calculate, and I will see. I want to show that, for example, in this problem, if I change it to a square root of x, in theory, everything that I'm going to do is possible, but I will not be able to follow and find the answer at the end. So this means that Newton's method was not just a simplicity of calculation. It was very elegant because it enabled us to calculate the integral of the functions that we couldn't do using this crude model. Okay, that's important. Okay, let us try to start with that. Okay, I want you to see what we do. In these kinds of problems, I would expect you to immediately start with the regular partition, because this Archimedes-Riemann criterion tells you that if you accidentally, or by educated guess or by experience, can come up with one sequence of partitions with that property, you are done. Okay, and the only one that we can work with, okay, in general, is the regular partition. So I would say that let n belongs to n, and let p sub n, let me write it, x naught, x1, up to xn, be the regular. Again, I'm saying that in that theorem, there is nothing force us to choose regular partition, but working with regular partitions is easier. And if I am lucky and it works for regular partitions, I am done. I don't need to find another one. So let P sub n be the regular partition of 0 and 1 with n plus 1 nodes, yes? So let me emphasize here that this is regular. Okay, so what I need to calculate, according to that theorem, I need to calculate this difference and then calculate the limit and send n to infinity. If I am lucky and this turns out to be 0, everything is done. Okay? So, let us do the calculations. But instead of calculating that in one go, let me do it separately. I calculate upper sum, and then I calculate lower sum, and then subtract them. That is easier. Okay? So, the first thing we will do is start calculating UF and PN. And it might be a good idea if I draw a picture here for you. So here this is 0, and this is 1, and this is your function. Because f of x equals to x is this function. Just a straight line. So what I am doing, I am partitioning this into n equal pieces, because I am considering this a regular partition. So it means that, for example, let me put some dots here and then some dots there. Let us concentrate here. So this is the kth interval. X sub k minus 1, x sub k. Okay? So concentrate only on this part now. Okay? Okay, so let us write this. The formula which I started today is sigma k goes from 1 to n, m sub k delta x sub k. Yes? And for L, I have sigma k goes from 1 to n, little m sub k delta x sub k. So let us calculate these things. The simple one is delta xk. Do I need equip these lengths with k? No, because all of them are the same. So can you tell me, so I would say that for every k in the set 1 up to n, if I ask you what is delta xk, what is your answer? Delta xk is the length of this interval. But what I have done, I have chopped my interval, I have partitioned my interval from 0 to 1 to n equal subintervals. Why equal? Because I intentionally using the regular partition. So what will be the length of each one of them? It will be the last number minus this number divided by n. Do you agree? That's just simply 1 over n. Okay, so this is done. I know this one here, I know this one. But can you help me to calculate m sub k? Here, my function is continuous. So in principle, m sub k is supremum of the values of my function on the kth interval. But because my function is continuous, there is no difference between supremum and maximum. So when I go to my picture, concentrate on this piece. Okay, so what is the maximum of your function in that interval? The maximum of this function is this much. Yes, do you agree? This is your maximum. So this is your m sub k. Okay, but what is that? Because this function is y equals to x. F of x equals to x. I want to know the height. If I want to know the height, I have to feed x sub k into my function, and I get the height back. But because this function y is equal to x sub mk is f of xk. Yes, it is f of xk. But because my function f of x is equal to x, so this is nothing except xk. Yes? And let us calculate little mk. So what is little mk? Little mk is this one. Okay? And that is exactly equal to f of xk minus 1. And this is exactly equal to fkx minus 1. Yes? But do you remember what is x sub k in a regular partition? X sub k is the first number, which is 0, plus k times the length of the subintervals. So it is just nothing k over n. Okay, x sub k is k over n. Here, x sub k minus 1 is k minus 1 over n. Okay, so I know m sub k is this one. I know little m sub k is that one. So everything is in order. Yes? So now let us calculate the difference. So the difference is so first let me write it as a sigma. This one minus that one, I can write 1 sigma. And then I can factor delta xk out. So do you agree? This is the difference. This is general formula. But now I put what I calculated inside the formula. So this becomes sigma. K goes from 1 to n. Delta xk is simply 1 over n. So let me write 1 over n here. M sub k is k over n. Little m sub k is k minus 1 over n. Do you agree? But this can be simplified a lot. So this becomes what? This becomes sigma, k goes from 1 to n. So do you agree the difference between them, the denominator is 1, the difference is 1. So it becomes 1 over n multiplied by another 1 over n. 1 over n squared. So what is this sigma? Can you help me? Sigma of 1 over n squared, but the counter is k and you don't see k there. So what is the sigma then? So this means 1 over n squared plus up to 1 over n squared, the constant term, n times. So this becomes simply n over n squared, which is 1 over n. Yes? So remember, if you have a sigma of a constant, k goes from m to n, it is n minus n plus 1 c. Or let me not make it hard for you. If it starts from 1 to n, it becomes simply nc. Yes? If it's a constant. Yeah? Of course, this is not something very mysterious, because this you can take this and write it a sub k. So this the a1 plus a2 up to an, but all of them are c. So when you add them up, it becomes nc. So that is the answer. And now I want to see if I am lucky that limit is 0 or not. You see, yes. Why? I calculate the limit of u fpn minus L fpn, n goes to infinity. But I already calculated this difference. It's an extremely simple sequence. N goes to infinity, and we know that this is 0. So this guarantees that my function is Riemann integrable from 0 to 1. So which theorem was that? This is 12.2. 12.2, part 1. But it doesn't tell me anything about what the value is. For the value, the second part will help me. This tells me that if I am lucky and I was able to find such a sequence of partitions for which this works, then the limit of each individual term is the integral I am looking for. Okay? And here I am lucky. By my regular partition, I got that partition for which the limit of this difference is 0. So this means that if I manage to calculate the limit of this one or the limit of that one, that will be the value for my integral. So here, which one is easier? It doesn't matter which one you calculate. So let us calculate u only. Okay? So here, I calculate u. So u f of Tn is equal to sigma k goes from 1 to n, instead of m sub k, I put k over n again. Instead of delta x sub k, I put 1 over n again. But I have to calculate this sum now. But this sum is not hard to calculate. This time, k depends on my counter, so I cannot pull everything out. But 1 over n, 1 over n, 1 over n squared, I can pull out. And k is left there. Yes? So now, this is a very famous sum. Have you seen it even in high school? Yes? This is the sum of 1 up to 2 up to n. This is an arithmetic sequence. So this becomes, if I don't know if you remember the formula or not, the formula for this sum is n times n plus 1 divided by 2. And then 1n and 1n are cancelled. So the answer simply becomes n plus 1 divided by 2n. So this becomes 1 over 2 plus 1 over 2n. So I don't need first brackets. Yes? And now let me calculate the limit. The limit of u f of Pn when n goes to infinity. What's the answer? The limit of this part is 0, the limit is 1/2. So this means that the integral of my function from 0 to 1 is this limit. So this is theorem 12.2, part 2. Yes? So this is why this is something you need to know for the exam as well. So one calculation of this type might be useful to know, or at least understand this, the definitions and everything. It doesn't matter. In this case, that it is granted that it is integrable, instead of calculating the limit of the upper sums, I can calculate the limit of the lower sums. If you do that, you will find the same answer. That's 1/2. So you see that it was just a matter of seconds to use Newton's method, but it was cumbersome if we wanted to do this. And then one more thing that is important to know, can you see if I change this to radical x, which part of it is not doable anymore? So you see that if I change it to radical x, in calculus, this is one of the simple questions that you don't even expect to be given to you in the exam because it's extremely simple. So this means that if I change it to radical x by the calculus method, you can immediately calculate it again. But do you see why I will be in trouble here? Which part of it will be troublesome? For example, look at the last one. This becomes a square root of k over n, if you calculate it for this one. And then I will get a square root of k. For this sum, I had a closed formula. But if I change this one to a square root of k, there is no closed formula for the sum of a square root of 1 plus a square root of 2 plus a square root of n. So then it means that I will not be able to calculate this sum so that after calculating it, I can calculate the limit. So this is not just a very, calculational ease. It was a genius of Newton who discovered that relation between this notion and the notion of derivative. Not only it helped us to calculate things much faster and more efficiently, but also be able to solve some problems which was not even possible by the crude definition of the integral. So that's important to understand. Any questions? Okay, so let us have a break now, and then we continue. Thank you.